Hello, everyone. So Pete told you all about the chip that we've designed that runs neural networks in the car. My team is responsible for training of these neural networks, and that includes all of data collection from the fleet, neural network training, and then some of the deployment onto that chip. So what do the neural networks do exactly in the car? So what we are seeing here is a stream of videos from across the vehicle, across the car. These are 8 cameras that send us videos, and then these neural networks are looking at those videos and are processing them and making predictions about what they're seeing. And so some of the things that we're interested in and some of the things you're seeing on this visualization here are lane line markings, other objects, the distances to those objects, what we call drivable space, shown in blue, which is where the car is allowed to go, and a lot of other predictions like traffic lights, traffic signs, and so on. Now, for my talk, I will talk roughly in 3 stages. So first, I'm going to give you a short primer on neural networks and how they work and how they're trained. And I need to do this because I need to explain in the second part why it is such a big deal that we have the fleet and why it's so important and why it's a key enabling factor to really training these neural networks and making them work effectively on the roads. And in the third stage, I'll talk about vision and LiDAR and how we can estimate depth just from vision alone. So the core problem that these networks are solving in the car is that of visual recognition. So for you and I, this is a very simple problem. You can look at all of these 4 images, and you can see that they contain a cello, a boat, an iguana, or scissors. So this is very simple and effortless for us. This is not the case for computers. And the reason for that is that these images are, to a computer, really just a massive grid of pixels. And at each pixel, you have the brightness value at that point. And so instead of just seeing an image, a computer really gets a million numbers in a grid that tell you the brightness values at all the positions.
A matrix, if you will. It really is the matrix.
Yeah. And so we have to go from that grid of pixels and brightness values into high-level concepts like iguana and so on. And as you might imagine, this iguana has a certain pattern of brightness values, but iguanas actually can take on many appearances. So they can be in many different appearances, different poses, and different brightness conditions against different backgrounds. You can have different crops of that iguana. And so we have to be robust across all those conditions, and we have to understand that all those different brightness patterns actually correspond to iguanas. Now, the reason you and I are very good at this is because we have a massive neural network inside our heads that is processing those images. So light hits the retina, travels to the back of your brain to the visual cortex, and the visual cortex consists of many neurons that are wired together and that are doing all the pattern recognition on top of those images. And really, over the last, I would say, about 5 years, the state-of-the-art approaches to processing images using computers have also started to use neural networks, but in this case, artificial neural networks. But these artificial neural networks, and this is just a cartoon diagram of it, are a very rough mathematical approximation to your visual cortex. We really do have neurons, and they are connected together. And here I'm only showing 3 or 4 neurons in 4 layers. But a typical neural network will have tens to hundreds of millions of neurons, and each neuron will have 1,000 connections. So these are really large pieces of almost simulated tissue. And then what we can do is we can take those neural networks and we can show them images. So for example, I can feed my iguana into this neural network, and the network will make predictions about what it's seeing. Now, in the beginning, these neural networks are initialized completely randomly. So the connection strengths between all those different neurons are completely random. And therefore, the predictions of that network are also going to be completely random. So it might think that you're actually looking at a boat right now, and it's very unlikely that this is actually an iguana. And during the training process, really what we're doing is we know that that's actually an iguana. We have a label. So what we're doing is we're basically saying, we'd like the probability of iguana to be larger for this image and the probability of all the other things to go down. And then there's a mathematical process called backpropagation and stochastic gradient descent that allows us to backpropagate that signal through those connections and update every one of those connections, just a little amount. And once the update is complete, the probability of iguana for this image will go up a little bit, so it might become 14%, and the probability of the other things will go down. And of course, we don't just do this for this single image. We actually have entire large data sets that are labeled. So we have lots of images. Typically, you might have millions of images, thousands of labels, or something like that. And you are doing forward-backward passes over and over again. So you're showing the computer, here's an image. It has an opinion. And then you're saying, this is the correct answer. And it tunes itself a little bit. You repeat this millions of times. And sometimes you show images, the same image to the computer, hundreds of times as well. So the network training typically will take on the order of a few hours or a few days, depending on how big of a network you're training. And that's the process of training a neural network. Now, there's something very unintuitive about the way neural networks work that I have to really get into, and that is that they really do require a lot of these examples, and they really do start from scratch. They know nothing, and it's really hard to wrap your head around this. So as an example, here's a cute dog, and you probably may not know the breed of this dog, but the correct answer is that this is a Japanese Spaniel. Now, all of us are looking at this, and we're seeing Japanese Spaniel, and we're like, okay, I got it. I understand kind of what this Japanese Spaniel looks like. And if I show you a few more images of other dogs, you can probably pick out other Japanese Spaniels here. So in particular, those 3 look like a Japanese Spaniel, and the other ones do not. So you can do this very quickly, and you need one example, but computers do not work like this. They actually need a ton of data of Japanese Spaniels. So this is a grid of Japanese Spaniels showing them, you need thousands of examples, showing them in different poses, different brightness conditions, different backgrounds, different crops. You really need to teach the computer from all the different angles what this Japanese Spaniel looks like, and it really requires all that data to get that to work. Otherwise, the computer can't pick up on that pattern automatically. So what does all this imply about the setting of self-driving? Of course, we don't care about dog breeds too much. Maybe we will at some point. But for now, we really care about lane line markings, objects, where they are, where we can drive, and so on. So the way we do this is we don't have labels like iguana for images, but we do have images from the fleet like this, and we're interested in, for example, lane line markings. So a human typically goes into an image and using a mouse annotates the lane line markings. So here's an example of an annotation that a human could create, a label for this image. And it's saying that that's what you should be seeing in this image. These are the lane line markings. And then what we can do is we can go to the fleet and we can ask for more images from the fleet. And if you ask the fleet, if you just do a naive job of this and you just ask for images at random, the fleet might respond with images like this, typically going forward on some highway. This is what you might just get like a random collection like this, and we would annotate all that data. Now, if you're not careful and you only annotate a random distribution of this data, your network will kind of pick up on this random distribution of data and work only in that regime. So if you show it a slightly different example, for example, here is an image that actually the road is curving, and it's a bit of a more residential neighborhood. Then if you show the neural network this image, that network might make a prediction that is incorrect. It might say that, okay, well, I've seen lots of times on highways, lanes just go forward, so here's a possible prediction. And of course, this is very incorrect. But the neural network really can't be blamed. It does not know that the tree on the left, whether or not it matters or not. It does not know if the car on the right matters or not towards the lane line. It does not know that the buildings in the background matter or not. It really starts completely from scratch. And you and I know that the truth is that none of those things matter. What actually matters is that there are a few white lane line markings over there in the vanishing point, and the fact that they curl a little bit should pull the prediction. Except there's no mechanism by which we can just tell the neural network, hey, those lane line markings actually matter. The only tool in the toolbox that we have is labeled data. So what we do is we need to take images like this when the network fails, and we need to label them correctly. So in this case, we will turn the lane to the right. And then we need to feed lots of images of this to the neural net. And neural net, over time, will basically pick up on this pattern that those things there don't matter, but those lane line markings do, and we'll learn to predict the correct lane. So what's really critical is not just the scale of the data set. We don't just want millions of images. We actually need to do a really good job of covering the possible space of things that the car might encounter on the roads. So we need to teach the computer how to handle scenarios where it's night and wet. You have all these different specular reflections, and as you might imagine, the brightness patterns in these images will look very different. We have to teach the computer how to deal with shadows, how to deal with forks in the road, how to deal with large objects that might be taking up most of that image, how to deal with tunnels, or how to deal with construction sites. And in all these cases, there's no, again, explicit mechanism to tell the network what to do. We only have massive amounts of data. We want to source all those images, and we want to annotate the correct lines, and the network will pick up on the patterns of those. Now, large and varied data sets basically make these networks work very well. This is not just a finding for us here at Tesla. This is a ubiquitous finding across the entire industry. So experiments and research from Google, from Facebook, from Baidu, from Alphabet's DeepMind all show similar plots where neural networks really love data and love scale and variety. As you add more data, these neural networks start to work better and get higher accuracies for free. So more data just makes them work better. Now, a number of people have kind of pointed out that potentially we could use simulation to actually achieve the scale of the data sets, and we're in charge of a lot of the conditions here, and maybe we can achieve some variety in a simulator. Now, at Tesla, and that was also kind of brought up in the questions just before this. Now, at Tesla, this is actually a screenshot of our own simulator. We use simulation extensively. We use it to develop and evaluate the software. We've also even used it for training, quite successfully so. But really, when it comes to training data for neural networks, there really is no substitute for real data. The simulations have a lot of trouble with modeling appearance, physics, and the behaviors of all the agents around you. So there are some examples to really drive that point across. The real world really throws a lot of crazy stuff at you. So in this case, for example, we have very complicated environments with snow, with trees, with wind. We have various visual artifacts that are hard to simulate potentially. We have complicated construction sites, bushes, and plastic bags that can go in, that can go around with the wind. Complicated construction sites that might feature lots of people, kids, animals, all mixed in, and simulating how those things interact and flow through this construction zone might actually be completely intractable. It's not about the movement of any one pedestrian in there. It's about how they respond to each other and how those cars respond to each other and how they respond to you driving in that setting. And all of those are actually really tricky to simulate. It's almost like you have to solve the self-driving problem to just simulate other cars in your simulation. So it's really complicated. So we have dogs, exotic animals. And in some cases, it's not even that you can't simulate it, it's that you can't even come up with it.
Yeah.
So for example, I didn't know that you can have truck on truck on truck like that, but in the real world, you find this, and you find lots of other things that are very hard to really even come up with. So really, the variety that I'm seeing in the data coming from the fleet is just crazy with respect to what we have in a simulator. We have a really good simulator.
Yeah, I mean, I think like simulation, you're fundamentally grading your own homework. So if you know that you're going to simulate it, okay, you can definitely solve for it. But as Andre is saying, you don't know what you don't know. The world is very weird and has millions of corner cases. And if somebody can produce a self-driving simulation that accurately matches reality, that in itself would be a monumental achievement of human capability. They can't. There's no way.
So I think the 3 points that I really tried to drive home until now are, to get neural networks to work well, you require these 3 essentials. You require a large data set, a varied data set, and a real data set. Mm-hmm. And if you have those capabilities, you can actually train neural networks and make them work very well. And so why is Tesla in such a unique and interesting position to really get all these 3 essentials right? And the answer to that, of course, is the fleet. We can really source data from it and make our neural network systems work extremely well. So let me take you through a concrete example of, for example, making the object detector work better, to give you a sense of how we develop these neural networks, how we iterate on them, and how we actually get them to work over time. So object detection is something we care a lot about. We'd like to put bounding boxes around, say, the cars and the objects here, because we need to track them and we need to understand how they might move around. So again, we might ask human annotators to give us some annotations for these, and humans might go in and might tell you that, okay, those patterns over there are cars and bicycles and so on. And you can train your neural network on this, but if you're not careful, the neural network will make mispredictions in some cases. So as an example, if we stumble by a car like this that has a bike on the back of it, then the neural network actually, when I joined, would actually create 2 detections. It would create a car detection and a bicycle detection. And that's actually kind of correct, because I guess both of those objects actually exist. But for the purposes of the controller and the planner downstream, you really don't want to deal with the fact that this bicycle can go with the car. The truth is that that bike is attached to that car, so in terms of like just objects on the road, there's a single object, a single car. And so what you'd like to do now is you'd like to just potentially annotate lots of those images as this is just a single car. So the process that we go through internally in the team is that we take this image, or a few images that show this pattern, and we have a mechanism, a machine learning mechanism, by which we can ask the fleet to source us examples that look like that. And the fleet might respond with images that contains those patterns. So as an example, these 6 images might come from the fleet. They all contain bikes on backs of cars. And we would go in and we would annotate all those as just a single car, and then the performance of that detector actually improves. And the network internally understands that, hey, when the bike is just attached to the car, that's actually just a single car. And it can learn that given enough examples. And that's how we've sort of fixed that problem. I will mention that I talk quite a bit about sourcing data from the fleet. I just want to make a quick point that we've designed this from the beginning with privacy in mind, and all the data that we use for training is anonymized. Now, the fleet doesn't just respond with bicycles on backs of cars. We look for lots of things all the time. So, for example, we look for boats, and the fleet can respond with boats. We look for construction sites, and the fleet can send us lots of construction sites from across the world. We look for even slightly more rare cases. So for example, finding debris on the road is pretty important to us. So these are examples of images that have streamed to us from the fleet that show tires, cones, plastic bags, and things like that. If we can source these at scale, we can annotate them correctly, and the neural network can learn how to deal with them in the world. Here's another example. Animals, of course, also a very rare occurrence, an event, but we want the neural network to really understand what's going on here, that these are animals, and we want to deal with that correctly. So to summarize, the process by which we iterate on neural network predictions looks something like this. We start with a seed data set that was potentially sourced at random. We annotate that data set, and then we train neural networks on that data set and put that in the car. And then we have mechanisms by which we notice inaccuracies in the car when this detector may be misbehaving. So for example, if we detect that the neural network might be uncertain, or if we detect that, or if there's a driver intervention on any of those settings, we can create this trigger infrastructure that sends us data of those inaccuracies. And so for example, if we don't perform very well on lane line detection on tunnels, then we can notice that there's a problem in tunnels. That image would enter our unit tests, so we can verify that we've actually fixing the problem over time. But now what you do is to fix this inaccuracy, you need to source many more examples that look like that. So we ask the fleet to please send us many more tunnels, and then we label all those tunnels correctly. We incorporate that into the training set, and we retrain the network, redeploy, and iterate the cycle over and over again. And so we refer to this iterative process by which we improve these predictions as the data engine. So iteratively deploying something, potentially in shadow mode, sourcing inaccuracies, and incorporating them into the training set over and over again. And we do this basically for all the predictions of these neural networks.